Hello, welcome to More Learn, More Teach, where I attempt to simplify the complex. Now that we know how to multiply matrices, we're going to talk about how you invert a matrix. So here I have a matrix. I have two two-dimensional vectors, the A vector and the B vector, with the x component, y component of the A vector, x component, y component of the B vector. I'm going to multiply it by something called an inversion. I'm going to invert this matrix, multiply that by itself, and I end up with what's called an identity matrix. The identity matrix is a matrix that only has a single one in a row and a column. So they're typically drawn with the diagonals all being ones. So this is analogous to, but not equivalent to, if I took a quantity, multiplied it by the inverse of itself, and got 1 using normal algebra. It's not exactly the same, but that's the way I keep track of it in my mind. Maybe that helps you out. All right, so I've replaced the inverse matrix with a new matrix, a C matrix. We are going to now solve for each element in this new C matrix. We're going to do that using our multiplication rule. So I will take the dot product of this row and this column, as we have here. So AX times C11 plus AY times C21 is equal to 1. Take the dot product of this row and this column. So AX times C12 plus AY times C22 is equal to 0. The dot product of this row and this column, BX times C11 plus BY times C21 is equal to 0. Dot product of this row and this column, BX times C12 plus BY times C22 must equal to 1. We have here our A-B vector matrix inverted. That's going to equal to this C matrix. So the equations we get out of this are that AX times C11 plus AY times C21 equals 1. AX times C12 plus AY times C22 equals 0. BX times C11 plus BY C21 equals 0. BX C12 plus BY C22 equals 1. So now I have a system of equations. I have 4 equations, 4 unknowns. I'm going to choose to do this in a 4x4 matrix. So here I have mapped out these 4 equations into matrix format. I have a 4x4 matrix multiplied by a 4x1 matrix, which will equal to this answer matrix. I spread it out to give me a lot of room here. For my first reduction, I'm going to take this first equation, I'm going to divide both sides of this equation by AX. What that looks like in our matrix is this first row, which was this first equation, divided by AX. So this row multiplied by this column is equal to this dot product, which is why this is the equation that is represented by this row multiplied by this column. If I divide both sides by AX, I divide everything in this row by AX. I divide the answer 1, 1 position by AX. I do nothing to this, the same reason that I would do nothing to the individual variable in the actual equation. And I end up with 1, 0, AY over AX, 0, and 1 over AX. Continuing on with our attempt to get everything to the left side of this 4x4 matrix to be a 1, I'm dividing both sides of the second equation by ax, both sides of the third equation by bx, and both sides of the fourth equation by bx. So this gives me a matrix that is 0, 1, 0, ay over ax. This became 0, 1, 0, by over bx, 0, 0, 0, 1, 0, by over bx, and 1 over bx. It's not quite our identity matrix, but we're getting closer. So I want everything in this diagonal to be a 1 for my identity matrix. So now I've reduced the leading term to where it's a 1, but now I need to remove this 1 and this 1. So we're going to do that by subtracting equations. So now I'm going to subtract this equation from this equation. When I subtract this equation from this equation, that 1 will go away. I will subtract this equation from this equation, which will remove this 1. And this works because this quantity is equal to this quantity as represented by the equal sign, which allows me to do that substitution. So I've done nothing contrary to any of the algebraic rules you've covered before. It just looks a little different because now it's in this matrix. So again, I'm going to subtract this row from this row and this row from this row to end up with something that's much closer to my identity matrix. We have now subtracted the first row from the third row. You must also subtract the 1, 1 from the 3, 1. We subtracted the second row from the fourth row. You must subtract the 2, 1 from the 4, 1 in order to make that work. And we're left with only content in the diagonals to the upper right. Turned everything to the lower left into zeros. Now I can divide through to give all of these to be 1. I have divided the new third row by by over bx minus ay over ax. I've done the same to the new fourth row. We'll end up with 1s on this side. I've created 2 identities from this matrix. What do I mean by that? I mean that remember that the 3, 1 of my answer is the dot product of the third row and the first column. These are all zeros, so the only thing I have multiplying is this 1 multiplied by this C21 is equal to this quantity right here. So this is C21. In the same way, this is C22. Simplifying the 3, 1 element, I have 2 fractions that I am subtracting. I need to have a common denominator. So I'm going to multiply each of my items being subtracted by a unit of 1 that will give me a common denominator. So in this case, I need ax over ax, and in this case, I need bx over bx in order to get ax by minus ay bx all over ax bx. Remember, if I'm dividing by a fraction, I invert and multiply. So this is the same as negative 1 over ax invert and multiply. I'll multiply by ax bx over ax by minus ay bx, reducing out my ax. It leaves me with negative bx over ax by minus ay bx. Doing the same for the 4, 1 position of the answer matrix. I have 1 over bx all over by over bx minus ay over ax. To get a common denominator, I'm going to multiply by 1 in the form of ax over ax and bx over bx. That gives me 1 over bx all over ax by minus ay bx over ax bx. Remember, you divide a fraction by inverting and multiplying, and I end up with ax over ax by minus ay bx. So I now have the identity of C21, which is negative b over ax by minus ay bx, and I have the identity of C22, which is ax over ax by minus ay bx. I still need to do some manipulations to get the identity of the other two. So now I'm going to multiply and subtract. So I'm going to multiply the 4th row by ay over ax and subtract it from here in order to remove this term. And I'm going to do the same for this row with this row to remove this term. So what does that look like? So for the first row, I subtracted the 3rd row multiplied by ay over ax. So that is this 0 multiplied by ay over ax, this 0 multiplied by ay over ax, this 1 multiplied by ay over ax, this 0 multiplied by ay over ax, this quantity, which is negative bx over ax by minus ay bx, all of that multiplied by ay ax. The same thing between rows 2 and 4. And I end up over here with 0 minus ax over ax by minus ay bx, all of that multiplied by ay ax. I have now accomplished my identity matrix. So the identity of C11 is this quantity. The identity of C12 is this quantity. The identity of C21 is this quantity. And the identity of C22 is this quantity. So let's reduce this to something that is more meaningful. So I take the 1, 1 term. I have 1 over ax plus, so that negative becomes a plus, bx ay multiplied through by the ay divided by ax by minus ay bx, all of that multiplied by 1 over ax. I did that so that I can have a common term here that I can factor out. So I'm factoring out this term here to give me this expression here. Now I will add these two. Again, I'll turn this 1 into something that's useful with a common denominator. This will be my common denominator. So that's this expression here. We can see that this term is the opposite of this term, ax by divided by ax by minus ay bx. All that divided by ax becomes by over ax by minus ay bx. The 2, 1 term is a lot easier. We have negative ax ay divided by ax by minus ay bx, all of that multiplied by ax. The AX's will cancel out, and I end up with negative y over AX by minus AY bx. This is what I'm left with. The identity matrix multiplied by my C1, 1, C1, 2, C2, 1, C2, 2 terms gives me this answer matrix, which means that the identity of C11 is this term, the identity of C12 is this term, the identity of C21 is this term, the identity of C22 is this term. Inverse matrix of AXAY BX BY, the inverse matrix of this is this 2 by 2 matrix here. So we have our inverse matrix is equal to these quantities that we just found. We see we have a common term in every element of our matrix. I can extract that out, and I have 1 over AX BY minus AY BX multiplied by BY, negative AY, negative BX, AX. This is also the inverse matrix of our original matrix. Turns out this denominator is what's called a determinant. We can see that if this term is non-zero, then this is a valid expression. If this term is 0, this becomes infinity, therefore it would be a non-invertible matrix. So, as I said, this is the determinant. Another way of finding the determinant, if I took my matrix and put these straight lines here to symbolize a determinant. So if I take a diagonal, I have AX and BY, AX times BY, and I subtract the other cross, AY BX, I get this determinant. So if I wanted to do a 3 by 3 matrix, if I want to invert it, it's the same process. But if I just want to look at the determinant, let's look at what determinant would look like for a 3 by 3 matrix. So here I have some matrix F, the determinant of matrix F. I've got my bars to indicate determinant. So it turns out that for this three-dimensional case, I'll be looking at each column of the first row. I will isolate each one of these terms and get a subdeterminant. Multiply that by that factor. So let's see how that works. So here I've shown for the first column, so for the F11, I block out the first column and the first row, and I'm left with F22, F23, F32, and F33. I take the determinant as we just saw for the two-dimensional case, and I multiply that by F11. I have F11 multiplied by the determinant of this submatrix, which is F22 times F33 minus F23, F32. For every even column, we have to subtract. So we have here the F12. So I block off the first row and the second column. I have negative F12 multiplied by the determinant of the terms that are left. So that's F21 times F33 minus F23 times F31. For the last column, block out row 1, column 3, take the determinant of the submatrix left behind. It's plus because it's the odd column. So I have plus f13 multiplied by f21 times f32 minus f22 times f31. So this is my determinant of the F matrix that I have here. I could continue this on for multiple dimensions. It just gets bigger and bigger and bigger. You keep shrinking these submatrices down. So maybe I'll do another video on that in the future. But that's kind of beyond the scope of what I'm working for here. Thank you for watching my video. Please like and subscribe. If you have any questions that I can help you out with, I'd be happy to try and answer your questions. Send me an email at morelearnmoreteach@gmail.com.